Let us now solve question number 22. So the picture given in the question is a 3D picture. Okay. So basically what they are saying is there are two cylinders. So one cylinder here like this, and then there is one gap here, then one more cylinder here. The total mass of this cylinder is m. Okay. So here this is spring coming like this, and this is fastened to a wall, and the whole surface in which the cylinder is resting is a smooth, not smooth in the sense there is friction here, so that this cylinder scale, as it rolls, it will be rolling without slipping. So there is an external force acting on the cylinder, right? So when there is external force acting on the cylinder and still it wants to roll without slipping, then you need friction. So that we discuss in system of particles in some other video. I'll try to revise it. Okay. Or maybe I will just explain quickly. So when we say a cylinder or a disc or a sphere is rolling without slipping on a horizontal surface, it means what? This point of contact has no velocity with respect to the surface. Meaning this point of contact is at rest with respect to the surface, and there are no forces trying to push it. So therefore friction here is zero. There is no need for any friction, right? So just because this pen is at rest on my hand, that doesn't mean the friction acting is static friction. Static friction acts when I try to push it, but still it is at rest. Then there will be a static friction required. So here, this body can roll without slipping, even without any friction. But if you apply some force here, here, wherever, okay, and then you are still wanting this body to roll without slipping, then you need friction to keep this point of contact at rest with respect to the surface. So in this problem, the cylinder will require some friction from the floor. So they are asking you to find the time period of this system. So if you see the picture this way, it gets too complicated. So the best way to imagine this is, you see from the side. So if this is the cylinder, you see from here, okay, this side. So let's say this is the cross section of the cylinder. This is the surface, which is sufficiently rough so that it can roll without slipping, and the spring is attached to its center. Okay, so this is more easier to follow. Okay, the radius of the cylinder is r, mass of the cylinder is m, spring constant of the cylinder is mentioned to be much k. So what will be the time period of this? So how do we solve this? Okay, so the best way to solve this is, see, first understand what's happening. This point is not going to slide on the surface because it is undergoing rolling without slipping. So what kind of motion would happen? Let us try to visualize. So right now let us say this is the equilibrium position. Okay. So once you compress it, and then you can't compress this way, okay, then the point will slide. So once you compress it this way and leave it, it will oscillate this way. Okay. So if it, even if it rolls, it goes like this, then it comes like this. Goes like this, and comes like this. Okay. So I hope you are visualizing it. Okay. So that is how it is performing simple harmonic motion. So let us try to solve this problem with the help of, there is some kind of angular SHM. So let us try to calculate the torque. Okay. So let us say right now this is the situation. So then I give it a small displacement. So it turns by a small angle theta. Okay. Then this point gets displaced here, right? By, if I say this is r and this is a small angle theta, then this distance by which the center moves this way will be r theta. So if the center moves by r theta, okay, are you able to understand this? So right now the situation is such that this line is perpendicular to the surface. As you displace it this way, the center will travel a certain distance, and since the angular displacement is small, this can be taken like an arc. So that arc can be written as angle times radius. Now if the center moves by a distance r theta, it means the spring gets compressed by r theta. So there will be a spring force in this direction, and that spring force will be k times the displacement of the spring, that is your r theta. Right? Okay. Now this force, once you leave, we'll try to create a torque. Let's calculate a torque about this point. So there are no forces, whatever forces, normal force, energy, they will not create torque about this point. All of them is passing through that point itself. So torque about O will be R perpendicular is R itself into this force, it is F. So that will be equals to K times R square, because once you substitute this F here, K R square times theta. What about moment of inertia of this disk about this end? So you know about center of mass, it is mr. This is solid cylinder, so it's same as disk, mr squared by 2. As long as moment of inertia formula is concerned, solid cylinder and disk has same formula. So mr squared by 2 plus m times h squared. So this distance is r. Because I want moment of inertia about this axis, because I calculated torque about this point. So that will be equals to 3 by 2 mr square. So torque, you know, can be written as I times alpha about O. Okay. So torque is K R square theta equals to moment of inertia about O is how much? 3 by 2 mr square times alpha. So alpha will be what? R square gets cancelled, 2k by 3m times alpha. 2k by 3m times alpha. So this is alpha, so 2k by 3m times theta. Again, you can see if theta is this way, angular acceleration due to the torque will be this way. Because the torque is this way, right? R is here, F is here, so R cross F will tend to produce rotation this way. So they are in opposite direction. So this will be your omega square. So time period will be 2 pi divided by omega, so the root over 3m by 2k. Okay, so it matches with option D. Let us say what would happen if I do a small change in this problem. In the sense, I will not connect the spring to the center of the cylinder, but let's say this is my cylinder. I connect it to this point. So now you have to be a little bit careful, okay? Again, the friction here is sufficient so that it doesn't roll, doesn't slip on the floor. It rolls without slipping. Now again the same story. So this right now this in equilibrium, let's say this line is here. So after a certain time, as it oscillates, it covers a certain angle theta, a very small angle theta. So now I'm not really interested in how much distance the center has moved. I'm interested in this distance. So this is your 2r now. So this distance will be 2r times theta. So spring force will be this way, K times the compression with 2r theta. Okay. So now I want to calculate torque about this point. Yes or no? So torque about this point will be this force K into 2r into theta. Force into r perpendicular is 2r, so it becomes square, this will become 4. And that will be equals to I times alpha. Moment of inertia of this about this axis will be how much? We have calculated, right? Here it is mr square by 2, this is will be 3 by 2 mr square. So once you have found alpha, it will be 8, 4 are 8, right? 8k by 3m theta. So this guy is your omega square. I did this little faster because it's a similar question like we did before. Okay.